here is the punctuated version of your text. In their central goal to get a handle on the first stars and universes that illuminated the universe, cosmologists are still lacking clarity. However, they are moving closer to illumination. One disclosure during a period that is the awesome inescapable end is the momentous disclosures by the James Webb Space Telescope, JWST, the $1 billion time machine that just completed its generally important year of insights. This was planned to capture the weak infrared shimmer of the universe's earliest brilliant articles. The Webb's vision wandered again into the early universe, a few 100 million years after the colossal explosion, allowing it to obtain more and better data about newborn universes than any other facility has collected at this point. Its passage of grandiose kid pictures has shown more plentifully than most researchers hoped. Recently, putative candidate frameworks in the early universe are jumping up in numbers that go against assumptions, with modest bunches considered to be doing this point. This has made analysts go ballistic. As Charlotte Brickley, an astrophysicist at the School of Copenhagen, said, "We genuinely weren't guessing this in the extended lengths of time following JWST revelations of incredibly distant early frameworks. Researchers and observers have been mixed in checking out these early observations. Could the pack of unusual, huge, and splendid early universes be a result, perhaps, of imperfections in the assessment of the telescope's fundamental discernments? If true, could they be checked out by standard cosmological models? Or perhaps are they the main clues that the universe is more bizarre and complex than even our boldest theories had ever anticipated? Furthermore, could the Big Bang Theory be off base? Join us today as we dive deep into how the James Webb Space Telescope is reshaping our understanding of the universe. Let's get to the feature. Understand the trouble and return to when the universe was believed to have been formed after the Big Bang. The infant universe began cooling a few million years later. The irritating plasma that filled space settled down, and electrons, protons, and neutrons combined into molecules, primarily neutral hydrogen. Things were quiet and faint for a period known as the endless dark ages. Then something happened. The majority of the material that flew apart after the Big Bang is made of something we can't see called dark matter. It has had a strong influence over the universe, especially at first. In the standard picture, cold dark matter, a term that refers to invisible or sluggish particles, was scattered about the universe. In specific regions, its scattering was denser, and in these areas it began collapsing into groups. Visible matter, meaning atoms, packed around the groups of dark matter. As the molecules cooled, they eventually densified, and the first stars were born. These new sources of radiation reionized the neutral hydrogen that filled the universe during the so-called reionization era. Through gravity, larger and more massive structures formed, creating a vast network of galaxies. Meanwhile, everything continued to fly apart. The universe was expanding rapidly. The cosmologist Edwin Hubble discovered during the 1920s that the universe is expanding. In the late 1990s, his namesake, the Hubble Space Telescope, found proof that this expansion is accelerating. Consider the universe as a piece of raisin bread. It starts as a mix of flour, water, yeast, and raisins. When you combine these ingredients, the yeast begins to grow, and the dough starts to rise. The raisins inside it, standing in for galaxies, stretch further apart as the dough expands. The Hubble telescope observed that this expansion is happening at a faster rate. The raisins are flying apart at a speed that defies their gravitational attraction. This acceleration appears to be driven by the mysterious energy of space itself, known as dark energy, represented by the Greek letter lambda. Plugging values for cold dark matter, ordinary matter, and radiation into the equations of Albert Einstein's general theory of relativity gives a model of how the universe evolves. This lambda cold dark matter, LCDM, model matches almost all observations of the universe. One method of testing this model is by examining the most distant galaxies. Recalling that in the initial few 100 million years after the Big Bang, the universe was simpler, its evolution was easier to investigate against predictions. Astronomers initially tried to see the earliest structures of the universe using the Hubble telescope in 1995. Over 10 days, Hubble captured 342 images of an empty-looking patch of sky in the Great Deep Field. Astronomers were astonished by the flood of galaxies hidden in the inky darkness. Hubble could see thousands of galaxies at various distances and evolutionary stages, extending back to much earlier times than anyone expected. Hubble continued to find some truly distant galaxies. In 2016, cosmologists identified its most distant galaxy, called GN-Z11, a faint smudge that they dated to around 400 million years after the Big Bang. This was incredibly early for a galaxy, but it didn't fit neatly into the LCDM model. Partly because the galaxy was small, with only 1% of the typical mass, and partly because it remained solitary. Astronomers needed a more powerful telescope to determine if GN-Z11 was an anomaly or part of a larger population of enigmatic early massive galaxies, which could help determine whether we are missing a key piece of the LCDM model. This is why the James Webb Space Telescope, JWST, was built, considered the largest and most powerful observatory ever launched from Earth. JWST was designed to revolutionize how we interpret the universe, positioned 1.5 million kilometers away from regular interference and cooled close to absolute zero by its tennis court-sized sun shield. The telescope features a giant segmented mirror and exquisitely sensitive instruments, designed to reveal details of the early universe never before seen. This promise was fulfilled as the first discoveries were made within weeks of JWST's full operation. JWST has seen galaxies very close to the earliest epochs of cosmic history, examined the atmospheres of exoplanets in unprecedented detail, and provided stunning new views of galaxies in our solar system. However, it's just getting started. JWST's vision ventures into the first few 100 million years after the Big Bang, allowing it to gather more and better data about early universes than any other facility has. The implications are nothing short of transformative. Webb's early revelations could rewrite the early chapters of cosmic history, concerning not just ancient galaxies but also our own existence here in the cosmic realm. As JWST researcher Mark McAfee, a senior advisor for space and exploration at the European Space Agency, said, "You build these machines not to confirm the model but to break it. You just don't know how it will break." Using a form of the Doppler effect to measure distances, this is akin to figuring out the location of an emergency vehicle based on its siren. The pitch of the siren sounds higher as it approaches and lower as it recedes. The farther away a galaxy is, the faster it moves away from us, stretching its light to longer wavelengths and making it appear redder. This shift, expressed as Z, indicates how far an object's light has traveled to reach us. One of the first papers on JWST data came from Naidu, the MIT cosmologist, and his colleagues, whose search algorithm detected a galaxy that appeared astonishingly bright and incredibly distant. Naidu named it Glass Z13, indicating its extreme distance with a redshift of 13, further away than anything seen before. The galaxy's redshift was later revised to 12.4, and it was renamed Glass Z12. Other cosmologists working on various sets of JWST observations reported redshift values from 11 to 20, including one galaxy called CHEER 1749 or CR2Z71, whose light seems to have left 13.7 billion years ago, just 220 million years after the Big Bang, barely a blink in cosmic time. These purported findings suggested that the prevailing LCDM model might be flawed. In the early universe, we didn't expect to see such massive galaxies. Chris Lel, an astrophysicist at the School of Portsmouth in England, noted that in a study published in November, researchers examined virtual simulations of galaxies as predicted by the LCDM model. They found that JWST's early brilliant galaxy candidates were larger than those that formed in the simulations. Some cosmologists and news sources claimed that JWST was breaking cosmology, but not everyone was convinced. One issue is that LCDM predictions are not entirely clear. While dark matter and dark energy are well defined, visible matter has complex interactions and behaviors, and nobody knows precisely what happened in the early years after the Big Bang. Those early times need to be approximated in computer simulations. Another issue is that it's challenging to determine the exact distance of galaxies. In the months following the initial papers, the ages of some high redshift galaxies have been reevaluated. Some were downgraded to later periods of cosmic evolution due to updated telescope adjustments. For instance, CHEER 1749 is found in a region of the sky containing a group of galaxies whose light was emitted 12.4 billion years ago, and Naidu suggests it could be part of this group, a closer intruder that might be filled with dust, making it appear more redshifted than it actually is. Naidu also says Cheer 1749 is unique despite its distance. It could be a type of galaxy we had little knowledge about, a very low-mass small galaxy that somehow accumulated a lot of dust, which is unusual for such distant galaxies. For these far-off galaxies, it was understood that the most definitive distance estimates would require JWST's powerful capabilities. JWST not only observes starlight through photometry, or measuring brightness, but also through spectroscopy, or measuring the light's frequencies. If a photometric observation is like a snapshot of a face in a crowd, then a spectroscopic observation is like a DNA test.